Hello friends, here in this video we will see a problem on double integration method. Here is the question. Determine the deflection at free end C for the overhanging beam ABC supported and loaded as shown in figure. Here the diagram of the beam is given. It is seen that the beam is supported at A and at B. Its end C is free. So this is the free end of the beam, which is the overhanging portion BC. So this is a case of overhanging beam. Now take capital E, Young's modulus for the beam material is 200 gigapascal and I is 13.5 into 10 raised to minus 6 meter raised to 4. This is the MI, moment of inertia value. Now here in the data I'll write down, we have to calculate the deflection at free end. So deflection is given by y suffix c, that is deflection at point C is what we have to calculate. Now for the solution of such a problem, the first thing should be we should know the support reactions, that is how much is the reaction at A and reaction at B. For that I'll draw this beam again in the solution part. So drawing the beam again, here I'll mark the distances which are given in the problem. Now here as we can see, this beam ABC is the overhanging beam supported between A and B. So here we need to calculate how much will be the reaction at A, RA, and reaction at B, that is RB. We have to find these two values. So now I'll say that considering the given beam under equilibrium and using the first condition of equilibrium, that is summation of Fy is equal to 0, where upward forces are positive and downward forces are negative. So we have RA and RB both are upward, so positive, RA plus RB. Then this UDL value is given as 3 kilonewton per meter. So if I convert this into point load, so it will be 3 into 3 and it will be acting downwards, so minus 3 into 3. Then we have 4.5 acting downward, so minus 4.5 is equal to 0. So therefore RA plus RB, this value comes out to be, it is 13.5, and I'll keep this as equation number 1. Now I need to find out RA. For that I will be taking moments at B. So the second condition of equilibrium is summation of moment about point B is equal to 0. Clockwise moments positive and anti-clockwise moments negative. So we have RA as clockwise. So RA into the distance is 6 meter from B. So plus RA into 6 because it is clockwise. Next, here we are having 4.5 kilonewton. This is the overhanging portion. It produces clockwise moment. So plus 4.5 into 2. Next we have this point load, which is UDL converted into point load, that is 3 into 3, and it is acting at half of 3, so 1.5 plus 2, that becomes 3.5 is the distance between this UDL when it is converted into point load from point B, and here it is negative because it produces anti-clockwise moment. So that is equal to 0, and here if I go on calculating this, I'll get RA value as 3.75 kilonewton, and putting this RA value in equation 1 I'll get RB answer as 9.75 kilonewton. So here we have both the values, that is we have found out RA and RB. RA 3.75 kilonewton, RB 9.75 kilonewton. Now after finding the support reactions, next I'll say that consider a section XX at a distance x from point A. So here I am considering a section from point A at a distance of small x. So here this is the section XX located at distance x from point A. Now after this I'll say that therefore by double integration method, taking moments of all forces on the left of section, we will take on the left of section and as well as on the right of the section, because on the right also we are having one value which is 4.5. So that will be, now on the, yes, we will take it only on to the left of the section. Now so we have moment at xx, it is given by EI d square y by dx square. Now some very important point here. See, whenever we are solving it by using double integration or Macaulay's method, and if the UDL is there in between the beam, that is if we see this is at distance DE, so we have to extend this UDL, extending this UDL up to the, we can say that end of the beam, we have to extend this up to the end of the beam, and in order to balance this UDL we should have one more UDL underneath the beam. It is like this, so that the effect gets cancelled out. This step is to be used if we have UDL anywhere in between the beam. If it is at the extreme end UDL, suppose if it has started from point A, then there is no need of extending this. But since it has started from D and ends on point E, we need to extend the UDL up to C, and to balance that another UDL value from bottom, and this UDL value from bottom will have same intensity as above, that is 3 kilonewton per meter. So now while I am taking the moments, we have RA into X. Here my consideration is clockwise moment positive and anti-clockwise moment negative. So we have plus RA into X. Next we have after this RB. Now RB is also producing clockwise moment and it is at x minus 6 this much distance. So we have plus RB into x minus 6. Next we have this UDL which is there on the upside of the beam at between D to C. So it is at x minus 1 distance. So I'll say that it is producing anti-clockwise moment. So minus 3 into x minus 1, that is I have converted the UDL into point load by multiplying it with x minus 1. Now this point load acts at half of x minus 1. So when I am taking the moment, that distance is into x minus 1, the half of that. Next the UDL which is there below, it produces clockwise moment and it is at x minus 4 distance. So it is plus 3 into x minus 4, and this is also acting at half of x minus 4. So now here I'll go on putting the values. EI d square y by dx square is equal to RA value was 3.75 into x plus RB it was 9.75 x minus 6 minus this will be 3 by 2 x minus 1 into x minus 1, that becomes x minus 1 whole square plus 3 by 2, and this is x minus 4 whole square. Now after reaching here, since I am solving it by using double integration method, so I'll equate this equation, I'll integrate it once. So therefore integrating once we get, now I'll integrate this equation EI into, first on integration we have EI, I'll write it as it is because it is constant value. Next, integration of d square y by dx square, that is dy by dx, it's equal to 3.75 into x, so the integration of x is x square by 2, and here I have integrated it for the first time, so the constant is c1. Next, plus 9.75 into x minus 6, so integration will be x minus 6 square whole square divided by 2, then minus 3 by 2, here we have x minus 1 whole square, so that becomes x minus 1 whole cube divided by 3 plus 3 by 2, x minus 4 whole square, x minus 4 whole cube divided by 3. So simplifying this, EI into dy by dx is equal to 3.75 by 2 x square plus c1 plus 9.75 into x minus 6 whole square by 2 minus 3 by 6 x minus 1 whole cube plus 3 by 6 x minus 4 whole cube. Now after the first integration I have got this equation, calling this as equation number 1. Next, integrating this equation again, we get EI, the integration of dy by dx is y, here we have 3.75 by 2, integration of x square is x cube by 3 plus c1 is c1 into x. Now since I am integrating for the second time, I have another constant which is c2, then plus 9.75 by 2 x minus 6 whole square, integration is whole cube by 3 minus 3 by 6 x minus 1 whole cube, integration is raised to power 4 by 4 plus 3 by 6 x minus 4 raised whole cube, that is raised to power 4 by 4. So on simplifying this, we have 3.75 x cube by 6 plus c1 into x plus c2 plus 9.75 by 6 x minus 6 whole cube minus 3 by 6 into 4, that is 24 x minus 1 raised to the power 4 plus 3 by 6 into 4, 24 x minus 4 raised to the power 4. So this is my equation second. Now here as we can see there are constants in the equation, so we need to find these constants. So therefore to find constants we need to apply boundary conditions. So the first boundary condition is at distance x is equal to 0, y value is 0, that is deflection is 0. At x is equal to 0, y is equal to 0. And the second boundary condition is when x is equal to up till b, that is 6 meter, at x is equal to 6 meter, y is equal to 0. So now after this we'll apply the boundary conditions one by one. So therefore, applying first boundary condition in equation number second, because we have the equation of deflection and boundary condition shows deflection y. So the first boundary condition is at x is equal to 0, y is 0. So here we have y 0, so left hand side 0 is equal to x is 0, so this first term is 0, plus c1 into x, this is 0, second term is 0. We have to reach only up to c2 for the first boundary condition, so therefore c2 is 0. Now applying second boundary condition in equation number second. So we have ei into y, and at x is equal to 6 meter, y is 0, so left hand side is 0. We have to replace x with 6 meter, so I'll go on putting the values. 3.75 into x cube, so it is 6 cube divided by 6, plus c1 into x, that is 6 c1, plus c2, that is 0, plus 9.75 by 6 into 6 minus 6 whole cube. This term will get cancelled out. 6 minus 6 is 0. Then minus 3 by 24. 6 minus 1 raised to the power 4 plus 3 by 24. 6 minus 4 raised to the power 4. Now after this, on simplifying this, I'll get the value of C1, and the answer of C1, it comes out to be, therefore C1 is minus 8.94. So here I have got, on simplification of this complete equation, C1 value is minus 8.94. Now if we look into the question, we have to find out the deflection at point C. So we need to put the values of C1, C2 in deflection equation. So here I'll say that there is no need of this slope equation because slope has not been asked. So I'll say that therefore put C1 and C2 in equation number second. So we have EI into y is equal to 3.75 x cube by 6. Now it is plus C1 into x, so C1 is minus 8.94 into x, plus C2 is 0, so no need to write that term. I'll copy the remaining terms as it is. So here this equation which I have got by putting the values of constant, equation number 3. So therefore equation number 3 is called as deflection equation, and from this equation deflection at any point in a beam can be calculated. So now here we have got the deflection equation, and if we look into the question, here we have to find the deflection at point C. So the distance is 1 plus 3, that is 4, plus 2, that is 6, plus 2, that is 8. So at x is equal to 8 meter, we have to find the deflection. So here I'll say that, therefore put x is equal to 8 meter in equation number 3, because we want the deflection. So I'll put the values here. Therefore EI into y is equal to 3.75 divided by 6. Here in place of x I'll write down 8, so 8 cube minus 8.94 into x, that is 8, plus 9.75 by x by 6 into x minus 6, so 8 minus 6 whole cube minus 3 by 24, 8 minus 1 raised to the power 4, plus 3 by 24 into 8 minus 4 raised to the power 4. So here on calculating this throughout, I am getting my answer of EI into y suffix c, because we are finding it at point C, minus 6.645, and here we want y suffix c. So I'll shift EI into the denominator. Now in this problem, E value is given, that was 200 GPa. So if capital E is 200 GPa, it means it is 200 into 10 raised to 6 kilonewton per meter square. I'll put this value, 200 into 10 raised to 6 into I is given 13.5 into 10 raised to minus 6. So therefore y suffix c comes out to be minus 2.46 into 10 raised to minus 3 meter, or I can say that it is minus 2.46 mm. And here the negative sign means that deflection is acting in the downward direction. The deflection is downward. So here if we look into the question, they had told us to find the deflection at point C. We had used the double integration method and find out the answer, and with this we complete the problem.